Hello everyone, welcome to Physics Fundamentals with Thomas Adeoye, and in this video you will learn what physical quantities are, why unit matters, and how dimensions can help us make sense of physical equations. And kindly journey with me. So to begin with, what is physics? I'm not trying to define physics, but this is just one of the facts about physics. It is an experimental science. So physics involves experiments, and experiments require measurements. So before you can do experiments, or in doing experiments, measurements need to be taken. Some measurements need to be taken. And when we say measurements, what are we measuring? What we are measuring is physical quantity. So physical quantity is any property of a physical system that can be measured and expressed in terms of numerical values and units. So look, for instance, if I'm interested in the average speed of a car during an entire journey, then I wanted to get the average speed, I have to measure some properties of the car. One of them is the total distance traveled by the car, and another thing I need to measure is the total time taken. So these two can give me the average speed of the car. So, and another thing I cannot but mention is the fact that physical quantities, they are completely described in terms of two things: a number, which is a numerical value now, and a unit. So a physical quantity without a unit is not complete. I mean, if you provide information about the numerical value of a physical quantity without mentioning its units, then this is incomplete. The information won't make sense. And let us take this as an example. If your friend, suppose you have a friend, and that friend of yours reached out to you and informed you that his dad credited his account with a sum of 6. I mean 6 as a figure. Of course, that information is not complete. You will be curious to know how to ask that 6 what? Is it 6 naira? If it is 6 naira, I bet you'll be disappointed because it's not worth celebrating. And or if it is $6, then this is fair enough, or 6 million naira now. So you want to know 6 what? Dollar, naira, the millions there, those are the units. So same is applicable if you're asked to measure the length of or the height of a pole. You don't just report your answer as 3 what? The people reading it want to know, is it 3 meters long, or 3 centimeters long, or 3 kilometers long? Perhaps the pole is just too high. So there is a need for you to indicate the unit of measurement, or the unit of a physical quantity, for it to make a complete sense. Do not forget where we started from. Physics is an experimental science. It involves experiments. We experiment in physics. It is not based on opinions. It is based on observations that are further, or that are verified now by doing the needful. Okay, so but and that's where we started from. It involves experiment, and experiment now involves measurement. And what is it exactly that we are measuring? Physical quantities. And for physical quantities now, they do not make complete sense unless you include their units. So let's move on. So physical quantities allow us to describe physical phenomena using numbers, not just words. Yes, we mentioned this. A value without the unit of measurement has no meaning. Yes, a physical value or a physical quantity without the unit of measurement has no meaning. Another thing I would love to mention is that any physical quantity there has to be a way of measuring it. Yes. Um, Height is a physical quantity because we have a way of measuring it. Force is a physical quantity. There is a way of measuring it. So for some of them, there may not be a way of direct measurement. But when you measure some other physical quantities from them, then you can get others. Now, just like speed of a car, by measuring the distance, the distance and the time, then you can get your speed. So love or beauty is not a physical quantity because there is no way we can measure that. So if your wife or your friend is you know very beautiful, you can't quantify it, or you can't say, okay, my friend is 60 watts. So that's just a joke. But beauty is not a physical quantity because it cannot be quantified. Okay, so moving on, we have classifications or types of physical quantities now, and there are just two. The first one is fundamental quantities, and as the name implies, it is the basic, like the basic quantities. They are the basic quantities. They are those quantities upon which other quantities depend. Some people will say upon which other quantities are derived, and it is true. We'll soon get to the other type of fundamental quantity, and I'll better explain this. But these are fundamental quantities, and the last time I checked, we have just 7. So length, and the unit meter, and that's a symbol. You can see mass there, time is there, electric current, thermodynamic, temperature, up to luminous intensity. Then derived quantities. So for derived quantities, and as the name implies also, they are obtained from combinations of 2 or more fundamental quantities. So they depend on fundamental quantities. Just like the other time, fundamental quantities do not depend on derived quantities. No, they don't. Okay. And moving on, we have dimensions, which is the last part. Now, dimensions, they are, what are dimensions? Dimension of a physical quantity is, it tells us it shows us how that physical quantity depends on other quantities, or we can say depends on other fundamental quantities. So what am I saying? I'll try to explain this as we solve, because we are going to look into some worked examples. But these are applications of dimensions or dimensional analysis. So we can use it to check the validity or otherwise of an equation. So with the help of dimensional analysis, we can get to know if a particular equation is valid. Because before an equation can be valid, one of the conditions it must satisfy is that it has to be dimensionally consistent or dimensionally balanced. So you get to understand this the more as we move further. We are going to solve problems. Physics involves solving a lot of problems, and that's one of the ways we thrive. Okay, so the second thing now is that we can use it to check the exact dependence of one quantity on another quantities or on other quantities in an equation. So you have a given equation, you want to know how this particular quantity, you single out a quantity and you are interested in how it is related to other quantities in an equation. You get to understand all this better when we solve. Now, worked examples. So we are going to be treating this. There are 7 questions here, and I'll try to look into them so that we can solve all of them. So we are going to go through this the solution of this 7 together. And okay, this is an exercise for you. You can check after the after you watch the video. Okay, so let's try to solve. Now for velocity now, if we are interested, we want to derive the dimension of velocity. So, and one thing you should know is that you have to know the formulas, like the formula of a particular quantity whose dimensions you are interested in. Okay, so for velocity now, we know that by definition, or yeah, it is velocity is the rate of change of position of an object with respect to time. So we can say velocity is equals to change in position, which is the same thing as displacement over time. Okay, I have to pause the video so that I won't waste time doing all this. So velocity is displacement over time, and displacement has the same unit as length. You can treat it as a length. I mean, yes, displacement, distance, height, breadth, width, depth. Okay, so the unit of length, as we all know, or as I mentioned now, is meter. So length is measured in meters, and this is the symbol meter. While time is measured in seconds. The SI units, let me be precise. So its time can be measured in minutes, in hours, in days, in years, but its SI unit is seconds now. So we have meters per seconds. Okay, and the same thing as ms raised to power minus 1. If this s, if it goes up, and based on the law of indices, the negative index law, so it becomes minus 1. So we now move on to this is the symbol, these square brackets. If you put these square brackets, or if you enclose a physical quantity using the square brackets, then it means you are interested in the dimension. Okay, so now the dimension will now be gotten from here. This is meter now. So for length, the dimension is L, capital L, and for time, this is seconds, unit of time, the dimension is T. So that becomes L to raised to power minus 1. So I forgot to mention something. The dimension of the fundamentals quantities, I mean their dimension. Okay, so I'll just write the dimension for each of them, I mean for length, in the next slide. I'll pause the video and write it so that we don't waste time on that as well. Okay, so I'll try and write the fundamental quantities and their respective dimensions. Okay, let me pause the video so that I won't take much of our time. And here we are. So for mass, the dimension is m. For length is capital L. For time, capital T. For current, electric current is capital I. And for temperature is theta. For what is this? J. This is for luminous intensity. whose unit is candela, then this J is the dimension. For amount of substance, then we have N. So now let's move on to some other examples. So example 2 is on force, the dimension of force. Okay, and here we are. So force, the formula is mass times acceleration. And acceleration is changing velocity over time. So we can proceed to write their unit. The unit of mass is kg, kilograms. For velocity, we could have written the formula again by just saying velocity is displacement over time. But since we derived the unit of displacement and we know it, that it is ms raised to power minus 1, then we can just have it here. Over the unit of time is seconds. So you now have kilogram ms raised to power minus 1, which is on top. These seconds can go up just like the other time using the negative indices law now. So if it goes up, it becomes x raised to power minus 1. So we now have x raised to power minus 1 multiplied by x raised to power minus 1. It will be x raised to power minus 1 plus minus 1. Plus times minus, that becomes minus. Then you have x raised to power minus 1 minus 1. And that gives x raised to power minus 2. And this is now kilogram meters per second squared. kgm x raised to power minus 2. Now to write this is the unit, okay, and to write the dimension, kilogram is the unit of mass and the dimension of mass is capital M. So we have capital M. Meter is the unit of length and the dimension is capital L. So the time seconds is the unit of time and the dimension is capital T. So we have mLT raised to power minus 2. So do not confuse meter, unit of length, and do not take unit of length of this m now, that is unit of length meter. Do not take its dimension as m, capital M. Please don't do that. Don't be tempted. So now let's move on to the third example, which is density. Okay, so density, the formula is mass over volume, mass divided by volume. And volume, we can have the formula to be length times breadth times height, as we have here, length times breadth times height. And the unit of length is measured in meters, breadth is measured in meter, and so is height. So we have meter times meter times meter, that gave kilogram divided by meter cube, and that becomes kilogram m raised to power minus 3. M cube, if it goes up, negative indices law. And we now have the density or the dimensions of density to be for kilogram now, unit of mass, capital M, meter, unit of length, capital L. So it is ml raised to power minus 3. And yeah, I know these are the easier ones. So let's move on to electric field. Yes, and as usual, the first thing is you write a formula. So electric field, the unit or the symbol rather is capital E. So you can write a formula for electric field. So there is no one formula for electric field, but we know that electric field it is the force. We can take it as force per unit charge. Yes, force per unit charge. That is force over quantity of charge now. That's F over Q. And from here, we can determine the dimensions. Okay, so force, I will not go over it again. I mean, we already derived the dimension of force, and if you have not forgotten, if you check the previous slides, you discover that force, it is kilogram meters per second squared. That is kgm s raised power minus 2. And because of that, I can just have it here that okay, for force it is kgm s raised power minus 2 over for charge now. Okay, well, here comes another thing. Here, force and charge, both of them are derived quantities. So I need to write, maybe I should have written the formula for charge first, but let me write it here. For charge, the formula is, what's the formula? Okay, charge should be, current is the rate of flow of electrons, or rate of flow of charge now, or charges um, per time, or what's it gonna, the rate of flow of charge, yes, and that should be I. That's why we have I, current, to be equals to quantity of charge over time. Yes, it should be Q over T. Let me be consistent with my unit. We can either use small letter q or capital letter Q. Okay, so this is current. Current is Q over T, and from here we can see that Q is actually equals to high T. Yes, Q, quantity of charge, is equals to the product of electric current and time. So if Q equals to IT, high is current, that is electric current, is a fundamental quantity, and the unit is ampere. So we can write it as capital A. The unit of current is capital A, and the unit of time is seconds. So that should be A times S. S is seconds. Okay. The next thing is to try to work around this. From here now, these two can go up. And pause this video. Okay, so and now we have here, what just happened was that this A goes up and we have a raised power minus 1. The seconds here also goes up and we have s raised power minus 1. Then this becomes kgm s raised power minus 1 minus 2 minus 1, that gives minus 3, and a raised power minus 1, and the dimensions will now be for kilogram, unit of mass, capital M, for meter, unit of length, capital L, for time, unit of for seconds rather, unit of time, we have capital T, then raised power minus 3, minus 2, minus 1. And for current, ampere, unit of current, that's capital I. Then the next question is the one for resistance. Okay, so another thing, okay, for this question, I want to find to derive the dimension of resistance. Okay, and this is one formula for, like in this formula, we can see that voltage equals to current times resistance. Okay, we could have used this, but we don't know the dimension of voltage. So although it's something that we can find, but I think it's easier and smarter to use this formula instead. Power equals to the square of current multiplied by resistance. So for power now, the formula is we can take it as work done over time, and work is force times distance, the magnitude of, okay, this is force times distance over time. Okay, although in the real sense, work should be the dot product of force and displacement, but we are going to discuss that once we get to vectors, probably in one of our subsequent videos now. So this is force times distance over time equals to the square of current multiplied by resistance. Okay, so if we make resistance the surrogate formula, we have force times distance over time divided by time times the square of current, I squared now. So we can now proceed with the units. For current, for force, we already found it that force is kilogram meters per second squared. Kg, that's the unit of mass. Meters per second squared, that's the unit of acceleration. So mass times acceleration multiplied by distance, unit of distance, is also measured in meters. Okay, divided by time in seconds, current in ampere. So we now have ampere squared. So these seconds can go up. Then we have kilogram meter squared per second squared. Now per seconds, s raised to power minus 1. As this goes up, using the what was it gonna, like, we can, this is just like 1 over s, and from negative indices law we have it as s raised to power minus 1, and same thing for a squared, which is a raised to power minus 2, and this becomes s raised to power minus 3, like that. So the dimensions of resistance will now be m, capital M for kilogram, L squared, t raised to power minus 3, I raised to power minus 2. So let's quickly do for the last one here, second to the last, but we'll just do one so that we can move on to some other examples that are not like this. Okay, so the one we are going to do last now before we move to some other examples is linear expansivity. Yes, I mentioned before that if you're asked to find the dimension or derive the dimension of any physical quantity, you want to know what is the formula. Okay, so linear expansivity is it is defined as a rate of change in length. It is change in length per unit length per degree rise in temperature now. So, and we can, that change in length, we can just take it as E. Okay, yes, we can take it as E, or we say L2 minus L1, where L2 will be the final length and L1 will be the initial length. But we can just, that change, since the change in length now is also measured in a meter. So, or better still, let's do this. Instead of using he, let's use let's write it this way. So we can have it as change in length. So the change in length per unit length and per degree rise in temperature. So let's take that one as change in theta. Okay, so we can write the formula like this. So change in length, its unit is also is meter. Okay, and per unit length, this one is also measured in meter. This is length and is measured in the initial length, and change in temperature is measured in what's the unit of temperature, thermodynamic temperature, Kelvin. So that's K. And of course, you should agree with me that this should cancel out so that we are left with just 1 over K. So 1 over K, and 1 over K, as usual, using negative indices law. So it can now turn to K raised to power minus 1. Then we can now write the dimension of linear expansivity as the dimension of temperature is theta. So that will be theta raised to power minus 1, like that. Okay, so let's move on to some other set of examples. Okay, so let's try something like this, more on dimensions. So the displacement of a particle in the xy plane is given by, so in this question now, displacement is given by, this is displacement x, is a displacement, is what's it called, displacement of a body along the x-axis. So, and it is given by at squared plus b, and y, I think y is given as dt cube minus e. Okay, so the question now says find the dimensions of a, b, and d. Okay, And this A, B, and D, I forgot to put there, they are constant. So we want to find their dimension. And T is time, measured in seconds, of course. Okay, and we know that displacement is measured in meter. So now let's consider how to do this. Okay, there are three questions here. The second question is on how we can use dimension or dimensional analysis to check the validity of an equation. So we have to check if this equation v squared equals to u squared plus 2s is a popular equation. Okay, we want to check if it is dimensionally consistent. And the third question is here. We'll solve these three and we'll end the class for today. Okay, so let's start with the first question here. Let's solve on the next page. So we have x, and it was given that x is equals to, okay, I paused the video. So we have x equals to 8c squared plus b. So what you should know is that, or what I want to tell you now, is that if you have any equation, so that equation, or in any equation, each term of the equation must have the same dimension. I mean, the dimension of each term must be consistent. What do I mean by that? This is x equals to 8c squared plus b. So the dimension of this x, there are three terms in this equation: this, this, and this. Do not make the mistake of thinking that this should be a two terms, like it should be two terms. No, it is not. It's just a single term. Okay, so there are three terms here: this, this, and this. So each of them must have the same dimension. So, and this applies to all, I mean, for all equation. For an equation to be valid, then the dimension of each term must be consistent. So it has to be dimensionally balanced. Okay, and luckily for us, we were told that this is displacement and t is time. Do not forget I mentioned that. So that means for me to find the dimension of b now, I don't need to stress myself, since I need the dimension of this and they must have the same dimension. Then I can say that dimension of x must be equal to the dimension of b. Okay, because each term, like this is the first term, the second term, the third term, each term must have the same dimension. So dimension of x must be equal to the dimension of b. Okay, but the question now is, what is the dimension of x? X is displacement on the x-axis or along the x-axis, and what is the unit of displacement? Meter. What is the dimension? Capital L. So this means that the dimension of b is capital L, and we have been able to nail this question now. For this one, dimension of b, we have to find the dimension of, I think, a, b, and d. Okay, so the next thing is the dimension of a. To find the dimension of a, same thing. So we can say dimension of x again is equals to the dimension of now it's not just a has something beside it, dimension of 8c squared. Okay, so dimension of x equals to dimension of 8c squared. And how do we go about this? Yes, we can now start. Dimension of x is, as usual, it is L. Okay, and dimension of this, which is let me separate them. The dimension of a is what we are looking for. Okay, and the dimension of t now, t is time, which is measured in seconds, and its dimension is capital T. So this becomes 8c squared. Okay, 8c squared, and you can see put this thing here. All right, So now the next thing is to divide through by t squared. So dividing through by t squared, we are going to have length here over, capital L over t squared equal to just a, just dimension of a. And finally, you can agree with me that, so the dimension of a now is, if t goes up, is L to raised to power minus 2, and that's that about that. And for the, okay, to mean the dimension of d, to find the to find the dimension of d, we are going to use this equation. It is y equals to, I think, dt cube then minus e. So we don't need to disturb ourselves with e. So same thing that we did for the previous ones is what we are going to do. So this has to be dimensionally consistent, meaning that dimension of each term must be the same. So that means dimension of dt cube must be the same as dimension of y. And what is y? Y is displacement along the y-axis. So, and what is dimension of displacement? Displacement, its dimension is capital L. So here, t is time, t cube. So we can now say that here the dimension of t is capital T. So we have it as t raised to power 3. Okay, and everything will be equals to the dimension of y. Here, what's the dimension of y is L. Okay, as just like we did, if you divide through by t cube, then we should have the dimension of t here to be equals to L over t cube, that is L divided by t raised to power 3, and that should give us L t raised to power minus 3. And we have successfully derived the dimension of A, B, and D. Okay, so let's check the second equation, or the second question. In the second question, we have to check if this equation v squared equals to u squared plus 2as. So one of the equation of a uniformly accelerated motion. Okay, so, and we want to check if it is dimensionally consistent. I said it before that this equation has to be dimensionally balanced or consistent before we can say that it is one of the conditions for it to be going to be valid. Okay, so all we just need to do is to find the dimension of each term, and if the dimension of each term is the same thing, then we are good to go. Then it is dimensionally consistent. Okay, so the first thing is to find the dimension of v squared. So we find the dimension of v squared, and we want to check if it will be equals to the dimension of u squared, and also check if it will be equals to the dimension of 2 multiplied by a multiplied by s. Okay, so, and in doing that, we need to know the unit of each of these quantities. Okay, so what's the unit of velocity? Of course, we derived that velocity, we found it to be meters per second squared. But now it should be ms raised to power minus 1 is what we should have, meters per seconds. Sorry, not meters per second squared, it's meters per seconds. Okay, but there is square here, so it's not just meters per seconds. Okay, so I pause the video, and here we have v, velocity is meters per seconds, and we square it. This is also velocity, initial velocity, meters per second, then the square. And acceleration, the unit is meters per second squared. And for this s, don't take it as the s is distance, please. So the S is distance and not seconds. So the unit is distance, the unit is meter. Now we have this to be m squared raised to power s raised to power minus 2, m raised to power 2 s raised to power minus 2. Here meter times meter gives m squared s raised to power minus 2. Okay, it's looking nice. For meters, the dimension is L squared 3 raised to power minus 2, L raised to power minus 2, 3 raised to power minus 2. But the question is, it seems there's a problem. And what's the problem? What is the dimension of 2? Okay, 2 is a number, a pure number. Okay, so I've not said this, but you should note it down now that dimension of pure numbers. Okay, pure numbers are dimensionless. Yes, or we can say their dimension is unity, 1. And if it is 1, 1 multiplied by this will give us the same thing. So because of that, we have m squared. Oh, sorry, I wanted to write dimension, not the unit. The dimension now will be so it should be, what is the dimension of m? That would be L squared t raised to power minus 2. And if you check through, you can see that each term has the same dimension. So we can now say that this equation is dimensionally consistent. I would say it is dimensionally balanced. Okay, and the last question for today will be on this. So the last question now is if G is equals to if G is equals to KRP, K multiplied by R multiplied by not R, I think it's rho, yes. K multiplied by rho, then we have to find the dimension of K. Okay, so where G is the acceleration due to gravity, this R is radius, and rho is density. So for this kind of question, just make K, all you need to do is to make K the Sawyer formula and write the unit for each of the quantity mentioned. So we have G to be R multiplied by rho. Okay, and so G is acceleration due to gravity. It's also acceleration. What's the unit of acceleration? Acceleration, the unit is meters per second squared, and that's ms raised to power minus 2 divided by the unit of radius. Radius is measured in meters, and density. Density, we already did this. Density, if you can still remember, you can check the previous slides. It's the unit is kilogram. The formula is mass over volume. So the unit is kilogram per meter cube, or kilogram m raised to power minus 3. Okay, so this is density. Of course, it's obvious this can cancel this, and we are left with s raised to power minus 2 on top, and kg can go up. Then we have kg raised to power minus 1. It's going up. Okay, using the negative indices law. It has for m raised to power minus 3. M raised to power minus 3. If it is m raised to power 3 and it goes up, it becomes m raised to power minus 3. Now that it is minus, what happens to it? Then the negative sign will cancel out, just like you might have guessed. Okay, so this is what we have. This is not supposed to be here. It's not supposed to be here. Okay, so then we can rearrange and say that the units will be, let kg come first, It is not necessary. I mean, it's not compulsory that it should be that way, but let's kg comes first. Then we have m cube here, and we have s raised to power minus 2 here. So that the dimension of k, the dimension of k now will now be equals to the dimension of kg. Kg, the unit of mass, its dimension is m. So we now have raised to power minus 1. Meter cube, the unit of length, so that will be L raised to power 3, and seconds, the unit of time, that's T raised to power minus 2. And that's it. We are done for the class. In the next video, you should watch out for that. We are going to solve some questions. I will display them. So in our next video, we'll try and solve this. We show the actual equation now, like the velocity of a transverse wave depends on this. Then how do we get the actual equation? So this question will also be solved, and if peradventure you solve those problems before the next video is released, you can drop your solutions on our Facebook page. I'll check and access it. So here, this is also another question that will be solved in our next video. So, and this is the YouTube channel. If you found this lesson helpful, kindly like the video and subscribe to the YouTube channel for more physics lessons. And do not forget to share your comments in the comment section. Finally, you should join the Facebook page for questions, discussions, and interactions. And on our Facebook page, where there is an ongoing weekly physics challenge. So the winner will be announced in the after 7 weeks, and who knows, you might be the lucky one. So you are encouraged to join the Facebook page. So thank you for staying true, and watch out for the next video.